You ever watch Machinima?
We're going to talk about
Are you getting your
later.
Far Cry Primal?
We're going to talk about net change and the net change theorem. Okay, so we've already kind of been working with this. All right, I kind of been hinting at it when we talk about like the meaning of some of these definite integrals, right? So in a context, the definite integral, right, with a basic understanding we know of the definite integral, it kind of is like finding the area underneath of a curve, right? We can find that for sure. But we can also use an integral, a definite integral, to identify the net change, okay? So net, obviously not like the thing that you throw at someone to like capture them, right? But it's like your net income, which is like how much you make minus, I think, like your taxes and stuff like that. Like your
fishing, like it's the amount.
Right, yeah. So like your gross income is like exactly what you get paid. Your net income is like what you get paid minus the stuff that the government has to take out. Okay, that's like called your net income because it takes some stuff away. So net change. Okay. Also, one thing I want to talk about, right? So net change. We saw this yesterday. I'll do it again though, right? So if I move to the right, 2 steps, and then I move to the left 2 steps, my overall or net change is 0, right? Because the positive 2 cancels out with the negative 2 going backwards, and so my net change is 0. So net change doesn't necessarily tell the entire story of what I did. It just tells from where I started to where I stopped that how much I changed as a result of that starting to stopping point, okay? We're going to talk tomorrow about the concept of moving out and back and like that being listed. That's called total distance traveled, right? Because that would be I traveled a total of 2, or I guess 4, 2 steps over, 2 steps back. So 4 would be my total distance traveled, but my net change is 0. So 2 related concepts, but not exactly the same thing, right? So, do you have a question?
I'm just going to point out that this is very, very similar to what we're doing.
To physics?
Yeah. It goes right along with what we're doing.
Nice, excellent. Okay, so.
We have Lagorda there.
What?
We have Lagorda.
What are we going to do?
Like what's the purpose? I guess there's lots of programs that the government funds that
You're here right now.
Public school, firefighter.
like there are things that we as citizens decide are important to have, and of course those things can't be free, so someone has to pay for them, and that means we pay for them. So we pay a small amount of money, and we put all that small amount of money together to then buy big things like planes and fund programs and things.
Will I get in trouble with the IRS if I don't fill out my W-2?
I don't know.
Probably not.
You should obey all federal laws.
I don't think the IRS is going to...
All right. So anyway, back on track with calculus here, folks. Let's focus here, all right? Saw something shiny, now you got back on track. All right. So, the definite integral of the rate of change of a quantity. So generally, when you're finding net change, you are going to be doing a definite integral to a rate of change. Okay, so net change is the definite integral of a rate of change of a quantity, and we'll call that quantity like just a generic kind of f prime of x. All right, gives the total, actually I'm just going to say, gives the net change. Okay, so again, the definite integral of the rate of change of a quantity, f prime of x, gives the net change. Okay. Or sometimes in particle motion, that's called the net displacement. Okay. Particle motion, I'll put that above it there. Okay, so in particle motion, call it net displacement sometimes. It means the same thing. So it gives the net change or net displacement in that of that quantity on the interval from A to B. On the interval, on the closed interval A, B there. Okay, yeah, question?
So this is sort of related. So net change can be positive or negative, but isn't
Correct.
Like gross? I don't know what the term in this class for like the gross change is.
No, it would not be gross change. Total distance traveled would be gross change.
Oh, isn't that an absolute value?
Yes.
Okay.
Yeah, we'll worry about that when we get there. Okay?
Where'd you learn that at?
So, in other words, the integral from a to b, right, of f prime of x, and that's just going to be equal then to f quantity, the f of b minus f of a then, right? We know that if we integrate a derivative, it takes us back to the original function, capital F. So if we integrate f prime, capital F prime, we should end up with capital F, and we evaluate using the fundamental theorem of calculus, f of b minus f of a, capital F of a, b minus capital F of a. Okay, now. We know this already, right? That's the first fundamental theorem of calculus, basically. But consider it now, if I manipulate this equation around some, so what do I mean by that? If I add f of a over, so this is an equation, right? So I can manipulate this like any other equation if I do the same thing to both sides. If I add f of a over here, I'll end up with f of b, capital F of b, is equal to f of a plus the integral from a to b of, and I'm going to run out of space, maybe not, it'll fit, okay, of f prime of x dx. All right, so again, this is something we know already, right? If we evaluate a definite integral, you integrate the f prime, becomes capital F, and you just plug in b and a. But then from this statement, we also then get this, right? If we just add f of a over, we end up with f of a plus that integral equals f of b. So why is this useful? Well, now, if we have a starting point, and we add to it the integral from a to b, taking us from a to b, all right, if we add to that the integral from a to b of the rate of change of this function, we then get to f of b, what f of b's value is. All right? So not needing to know the function, just knowing the function's rate of change and an initial point on that function, we can then find another point on that function. Right, a question?
So the second equation, essentially, you're taking that first equation and moving f of a over.
We add f of a over.
It would be like f of b equals f of a plus f of b minus f of a.
Say it one more time, sorry. F of b equals,
F of b equals f of a plus then that same f of b minus f of a, the f of a just cancel out.
correct. Yeah, that's what it's going to work out to be. That's what it would work out to be, yes. But the idea is that we, essentially, yes, you can see that yes, that's how it ends up being equal, yeah. But this is important. You'll see how we're going to use this in a second. So we can have some initial amount, or starting point, we can even say, or a starting point, okay? We're going to add to it then, this will add the net change from A to B, and then that yields the kind of like ending amount. Sorry, no, I'm like blocking. Okay, so you see that we have this kind of like starting point. We add to it the integral to kind of accumulate the change between A and B. So we use this to find the change, and then adding that to our original point gets us to then the final point. Okay, that's the idea. So let's go ahead.
So is the initial amount going to be like a number?
Yes, it'll be a value, and we're going to actually look at one right now. So let's see a problem here, and you can kind of see it in action. These are normally given in a context. You're normally given some sort of like what I would call, what you might call a word problem, right? Because there's a context to it. So, for example, a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. So you can see that our rate of the chemical flowing into the storage tank, our rate is not a constant rate, right? It's depending on what time it is. The further you go in time, the more the rate will be, the increase, the greater the rate will be. Okay? At time t in minutes, okay, so time is in minutes. And where 0 is less than or equal to t is less than or equal to 60. Okay. Find the amount of chemical that flows into the tank for the first 20 minutes. All right, find the amount of chemical that flows into the tank for the first 20 minutes. Okay, so there's our situation. Are we given an initial amount of chemical that's already like in the tank, for example?
No.
We don't know that, okay? All it says in the directions here is to find the amount of chemical that's flowing into the tank. So the tank may already have chemical in it, or it may have this chemical in it, may have something in it, it may not, though. We don't know. And so we're not going to worry about that, because all it says is just tell us the amount of chemical that's flowing into the tank for that first 20 minutes. So it's not caring about how much we have initially, so we don't need to worry about starting with this initial amount and then adding the integral. We're just going to worry about finding what the net change is. How much of the chemical is flowing into the tank in that first 20 minutes. So we're only going to worry about this piece, the net change itself. So we're going to integrate from what to what?
0 to 20.
0 to 20, right? Connie, you have a question?
Would the tank start with 180 for the chemical because it's 180 plus 13?
So this is the rate of change of the chemical flowing in. So at time t equals 0, it's 180 liters per minute, but then as the time goes. But that's the initial, it's like, this is not the initial amount of chemical, this is the initial rate of change of the chemical flowing in. So at time t equals 0, it will be 180 liters per minute, not just straight up liters. You see what I'm saying? The units would be liters per minute. So it's just the rate, the initial rate is that. Okay, good question though. All right, we don't know how much chemical is actually in there to start out with. All right, 0 to 20, and we're going to integrate what?
180 plus 3t.
The rate, yes, integrate the rate, 180 plus 3t. All right, and then we're going to do that with respect to t, obviously.
Should we denote this as f of t?
If you want to, or technically f prime of t, I would say. The function is f prime of t. So there's our integral. All right, so this is the rate. Okay, and then there's our time interval. And normally it's over an interval of time. Okay, and then that'll yield a net change. So let's go ahead and do this. All right, so it's pretty much easy to integrate there. Oh, question, yeah?
Well, couldn't you also sort of figure out the initial amount if you took the antiderivative of 180 plus 3t, because if that's liters per minute, wouldn't the antiderivative just give us liters?
If you integrate that, it would
be liters per minute.
It would still be the water
Per
coming
minute.
in. at that
Because
point.
I'm thinking like position, velocity, acceleration. When
But it would
the
just
same.
be 0. You're just saying
Yeah, it would be
0
0.
coming into the tank.
Yeah. It would be like, again, when you're integrating this, this is not the rate of change of the volume of the tank, although technically it's technically the rate of change of the volume of the tank,
Yeah.
but it's the rate flowing in, not necessarily because again, we don't know what the initial amount is. So right, at 0 it would be 0 according to this, but we don't know if there's a starting, because of that plus c at the end,
Yeah, we would.
that's the thing.
Yeah.
When we integrate that, we would have that plus c, we wouldn't know what that starting amount is, again, because we're not told, so we just gotta. So anyway, there it is integrated, and again, it's a definite integral. We don't have to worry about that plus c, but don't forget, right, if it's not a definite integral, if you don't have limits of integration, you should put it in plus c here. Since we have a definite integral, that we're just going to evaluate now from 0 to 20. Okay. So we evaluate that, and that's pretty much, let's see here, it's not going to be too bad. We'll plug in the 20 upper limit in for t. Okay, right, minus the lower limit. We already know what that's going to be, though. What's the lower limit going to equal?
0.
Yeah, it's just going to be 0, right? Okay. And so again, if this were a free response question, you circle that and you're done, okay? Like I said, we already know this bottom part's going to equal 0, and so it's a matter, let's see, 120 times 180 is what, 3,600, I think. And then 20 squared is 400. Half of that is 200 times 3 is 600.
4,200.
And so 4,200. And 4,200,
Liter.
what?
Liters.
Okay, why liters?
Because it's already per minute, like minute times liters per minute.
Okay, yeah, so you look here, right, we took liters per minute, which is the rate, and we integrated that. All right, liters per minute, and we integrated that, right? We took liters per minute, and we multiplied by, you know, a certain amount of time here. This little dt is like a change in time, so it's like liters per minute times the kind of thing in minutes. And so, yes, it results in just liters.
What?
Just liters. Okay. That is the net change. That is the net change. 4,200 liters. All right. So, questions on that? Are we all okay with that? So let's call that letter A, and then I'm going to say letter B then. Okay. How much chemical is in the tank after 20 minutes, after the first 20 minutes, I should say. If the tank started with 1,000 liters. Okay. So there's a different question, right? How much chemical is in the tank after the first 20 minutes if the tank started with 1,000 liters?
That's the equation we found.
So what is it, Tyler? 5,200 liters, yeah. Okay. Why is that? We start with 1,000 liters in the tank. We have a rate of change of chemical that's flowing into the tank at this rate, and from 0 to 20 minutes then, if we integrate that rate, we get the amount of chemical that's flowed in. All right? So what does that mean? So basically we're taking that 1,000, okay, that's at time t equals 0, right? It starts, it's like an initial amount, t equals 0, we have 1,000 liters already in the tank, right? It starts with 1,000 liters in the tank. We're going to add to it the integral from 0 to 20 of the rate at which chemical is flowing in, 180 plus 3t, dt. This is like the change from 0 to 20. And then that equals, so we start the initial amount, we add the change, and then that gives us to our final amount. After 20 minutes. Okay? So we could say something like the tank will have 5,200 liters of chemical, or 5,200 liters, yeah, of the chemical. After the first 20 minutes. It's important to specify the first 20 minutes here, because 20 minutes, just saying 20 minutes could refer from time 40 to 60, from time 20 to 40, from time 35 to 55, you know, we don't know. So it's important we say the first 20 minutes. It's the first 20 minutes because it's the time 0 to time 20. Okay? Right? Questions on any of that? Is that making sense? Yeah.
So we could have done this in part A after we found 4,200 liters to also find the initial, right? Because now we had the net change and the ending.
So we could have done this in part A if we had been given that piece of information in part A, yes. But in part A we didn't have that yet, so we needed that initial amount there from B to then say that, okay? Typically, folks, this is the way that an AP style question is going to ask this, is they will subtly throw in the fact that there's an initial starting amount in like an earlier sentence, then they'll tell you what the net change is. So you guys are like, all right, net change, got it, I have to integrate from this time to this time, and then you'll end up and give me just the answer from the integral, this, but you'll forget to add in the fact that, oh, later on they told me that there was already 1,000 liters of something in the tank. So don't forget, like, keep your eye out for those, like, an initial amounts. Sometimes they only will ask you for the change, the net change, like they did here for A. We only ask for the net change. Sometimes, though, they will give you a starting amount and ask for how much chemical is in the tank. So be careful of just giving the rate of change of it, or the amount of change, the net change. Check to see if there's not an initial amount or something. All right. Now, we can do this in a variety of other ways. So, let's do another example here. Here we'll do more abstract, so not in a context. So let's say this: given that f of x, a capital F of x, is the antiderivative of lowercase f of x, so with that little statement, blank is the derivative of blank. Yes, lowercase or uppercase? Lowercase f is the derivative of capital F. So capital F prime is f of x. If I find capital F prime, it's the same thing as lowercase f. All right, that's what that means, right? This thing is the antiderivative of this thing. That means if I integrate this, I get this. So if I take the derivative of this, I get this, right? So we have to be comfortable with going backwards and forwards now. If this is the antiderivative of this, that means the derivative of this is this, okay? Integrating gets you to this, taking the derivative gets you to this. That's what that statement's saying, okay?
Which one's the original?
That is chicken or the egg. Which one came first?
Yeah, the derivative.
Okay, in our case, since we learned about the derivative first, you might say then, I guess that, well, actually, I don't know. I guess, yeah, it really depends. You could, I guess, but then you would really get into like some 1984 kind of stuff there, where it's like double plus good, you know, you'd be changing words around, but redundant things. Anyway, okay, f of x. We're going to give some other information here. Capital F of 2 is equal to negative 3. All right, let's stop playing games with the pen cap, please. And lowercase f of x equals 2 square root of the arctangent of 3x plus 5x cubed. Okay? Find capital F of 5.
What? Something tells me the equation is not important in this problem because it's overly complicated.
Exactly right. Okay. Good intuition there. All right, so let's kind of like just digest this a little bit, what we're being asked to do. We ultimately want to find the value of capital F of 5. We are not told what capital F's function is. We do not know what capital F's function is. We do know what about capital F, though?
At 2 is equal to negative 3.
Okay, at 2, it's equal to negative 3, and we know something else about capital F. Its derivative is equal to what?
2
F of x, which is 2 square root arctangent. So this is the derivative of capital F right here. Okay, so we could integrate this and then just plug in the 5. Once we figure out what the C value is, right? We'd integrate this and then we'd plug in the C value, plug this in to get the C value, and then plug in 5 once we found the C value. Okay. What's the problem with using that that method?
That sucks.
We do not know how to integrate this. We cannot integrate this. Okay? And in fact, ABBC, for the BC kids, will not know how to integrate this either. This is impossible for us to integrate. Okay? Using our tools. So, how do we do this problem then? Well, we can use our calculator, yes, but how are we going to use our calculator? Because our calculator won't give us the function. So, for example, we can integrate this and get a value, but if we can't integrate this and get a function so that we can then plug this in. So, we're going to go back to this. We have an initial amount, don't we? What's our starting point that we know on F, capital F?
F of 2 is negative 3.
F of capital 2 is negative 3. So we know F of capital 2, we want to find what F of 5 is. So to get from 2 to 5, we're going to add, okay, the integral from what to what? If I'm at 2 and I want to get to 5, that means I need to integrate from what to what?
2 to 5.
2 to 5, right? I got to go from 2 to 5. All right. So I have my starting point of capital F of 2. Okay. I want to then add the integral from 2 to 5. That will accumulate the amount of change in my function to then get me to f of 5. Right. What's the thing I want to integrate here, though?
We don't know.
We do know we want to integrate here. It's this.
Yeah.
The rate of change. Remember, this is capital F prime of x. So this is the rate of change of capital F. So if I integrate the rate of change, I get the net change, the amount of change that's happening between 2 to 5. If I integrate from 2 to 5, I get the net change that's happening from 2 to 5. So I'm going to integrate this thing. 2 square root arctangent of 3x plus 5x cubed
So, is that just our answer then?
dx.
That is our answer?
Well, this is how we're going to find our answer, then yes.
Because we can't integrate that, so therefore we just plug in F2 negative 3.
We can use our calculators at this point.
Oh, okay.
We're going to use our calculators. Okay? So yes, now, go ahead, folks. I want you to use your calculator. Again, we know that capital F of 2 is negative 3. So negative 3. All right, and then you're going to type it in. Now, my pretty calculator, well, I'll let you go ahead and do that. So go ahead, with your calculators, go ahead and evaluate that integral using your calculators. Okay, however you choose to do it. Remember, you can use y1, and then do vars, y1 like that, if you want to integrate that function and from y1.
Will be a decimal answer.
Oh, yeah. Oh, yeah.
Was it
Yes, fn int. Yeah, so it's like math 9, I think. Yeah, math 9.
I like it. I like it a lot.
I like it a lot.
Like it a lot.
Yeah, 2 times the square root.
Arctangent and the same as...
Make sure you're set to radians, physics friends.
Missed that. Wait.
Hey, I warned you, didn't I? That's right.
Good thing I could just hit enter and do it again.
Sorry. Say again. Sorry.
Yes.
Yes, correct. Second tangent.
So, my sister's balaclava's not going to be here in time.
All right, I'm going to come around and see how we're doing here. Typing this thing in calculator.
She typed me.
I hope I did it right.
Boom.
Okay,
Now, we have to add this value, right?
Nope.
What'd you get?
Nope.
Right?
I want to
It's lower limit, upper limit. Try 2 to 5.
again tomorrow.
No, it didn't work so.
I didn't buy one of those. So, can I borrow one tomorrow?
I'm gonna get your parentheses.
Okay, perfect. Yeah.
And I'll wear my green one.
I think there's one more there.
I'm gonna have to change
and
stuff
then
3 times.
It works. But you still...
All in the space like 20 minutes.
Oh, ambassador. Yeah, we can wear an ambassador shirt.
Oh, we
don't
might
have
have
ambassador shirts. Yeah, we do.
We have the Buttwood polos.
Yeah.
Ones that we got that are like from 1943.
Arctangent. Oh, you didn't close the arctangent parenthesis in the right spot. So not here, but there. And then, yeah. Okay, now, Hannah, what I'd recommend you do, rather than trying to type it all in your function, this one is really hard to see, type it in your y1. So you go here, type 2 square root tangent 3x close parenthesis plus 5. You see, I think it's easier
I'm
for you
thinking
to
that
read
song here comes to boom.
not correctly. And then, math 9, bars, y bars, function y1. So you see it's using just y1 in there, comma, x, comma 2, comma 5. See how much easier that is? And it's easier for you to then keep organized that function. Not have to worry about all the parentheses. Yes.
Okay, well, first of all, you used the wrong command.
Why you say that?
Deriv, you want FN in.
I knew there was something wrong with that.
Okay, number 9, that's
Oh,
not,
yeah, that was forgetting.
I recommend you type it into your Y1.
Okay.
Type the function into your Y1 and then use bars, Y1.
Yo, boy, how'd you get 4 points? I got 40.
I got one.
You did? How am I getting
The
good?
3x, only arctangent of 3x.
Because it's tangent negative 1 to 3x.
If you did it, tangent negative 1.
Oh, I didn't do the 2.
How is this the?
I don't think that would matter.
I don't think they want to.
Yeah.
That should do it.
2 square root.
Okay, so negative 3 plus math. Oh no.
Get it okay?
2 math.
Get over your square, you gotta insert that.
5, 2.
Okay, so hang on. First of all, you're using type your function. Because it's be 2 times, so here's how you think. You want to put the square root right after the 2, you're going to have your cursor, put it right at the 2, and second, delete. And you see the same thing for insert. Now if you type in the second square root, it's like
Root.
I didn't know Pennsylvania. And it should be tangent, arctangent of the x.
1, 3,
Close bracket, it's like
It's right there.
Wait,
No,
yeah,
that goes up back. How do I do that? I don't know.
Okay. Now you go back.
Yeah, but how do I do
You
that?
want to go FN in, I can do. Okay, we're
I can't do that.
I can't drive anywhere.
Look.
Okay.
Hold up.
So bars, Y bars, Y1. So now whatever's your Y1, it's going to be X, integration. So comma 2, comma 5.
Close, plus 5, 3,
Boom.
close.
All right, everyone's got this okay? No one else needs any help?
Okay, so the final answer then is 90.218, right?
I did not get that.
Nope. Final answer is 87.2186 because we have to add the additional amount there. Okay, we have to add the initial amount. So the initial, 9.
Is 3x, is
Where'd you
only
get
3x
Oh.
with arctangent,
Wait,
or
how'd
is
you get
it 3x plus?
90.219?
The integral from 2 to 5 of 2 times the arctangent of 3x plus with 5x cubed is 90.219. Guys, let me point out something real quick here. I saw a few people make this mistake. You might have done the same thing. If you took this as arctangent of the entire quantity here, that's not what this is saying. This is saying arctangent of 3x, close parenthesis, plus 5x cubed, okay? Let me make this very clear. If you have an arctangent or a tangent or a sine or a cosine, whatever, one of those like trig functions, inverse or not, okay? If you have a trig function, if there's a sum, there will be parentheses around it so that you see the sum is included. If it's simply a product, then it's just the product that's included, and then this is on the outside, okay?
I got 87.2.
So then, yes, the final answer should be 87.219 for your final answer. That is the final answer, okay? So, again, the reason why I emphasized the no, that this is not the final answer here, is because the final answer is for us to find capital F of 5. We just did right here. Let me show you some things. Yes? Tyler, you have a question? All right, I'll come take a look at it in a second. Let me show you something else. Folks, if you, in your calculator, you can type in literally -3 plus, and watch, I'll even do it with the other way, the ugly way, since I think most of you guys have the ugly way. All right? You can do -3 plus the function integration here, and I'm going to go, again, I think I have it I don't have it. All right, I'll type the whole thing in here real quick. Sorry, 2 square root of arctangent 3x, close parentheses, plus 5x to the third, close parentheses there. All right. Bars, y bars function, y1, comma x, we're integrating with respect to x, comma 2 to 5. Okay, if I hit enter, it takes care of all of it for me. It adds the initial amount plus the function, so you can get your final answer in your calculator without having to worry about, then doing that last step. You can do it all at once. Boom, there it is. Okay? All right. Connor erased it. Great. Okay, well.
I was trying to help him out.
Nothing that before.
Well, I got rid of the problem.
Problem's gone.
I'm trying to make sure.
All right, well, Tyler, I'll, later in class, we'll have you try it again, okay? I'm going to move on though real quick. All right, so you guys, I want you to try this. Here we go. Try. All right, given capital F of x is the antiderivative of f of x, lowercase f of x. Capital F of 9 equals 3, and little f of x equals 4e to the sine of x minus 2 all over 2 plus 5 to the x. Okay, so again, that's e to the sine of x minus 2. That it's not sine of the quantity x minus 2, it's sine of x, then minus 2. That's all in the exponent, by the way. It's e to the power sine of x minus 2, okay?
I like it.
I want you to find, ready for this, capital F of 5.
Is that sine of x separate from the minus 2 or the sine of x minus 2?
It's sine of x minus 2, not sine of the quantity x minus 2, sine of x
Okay.
minus 2. Sine of the quantity x, and then minus 2. All right, now I want to point something out here real quick. So you guys are going to start this, but I just want to point one thing out just to kind of help. Okay, this is just like the problem we just did, okay, except in the original problem we did, we started at capital F of 2, and we wanted to go to capital F of 5. So our initial amount was at capital F of 2. We added the integral from 2 to 5 to get capital F of 5. Here, where are we starting? At capital F of what? 9, and we want to go to what? Capital F of 5, kind of like going backwards, right? Okay, so our limits of integration should be from what to what?
9 to 5.
9 to 5. 9 to 5. Working 9 to 5. Working 9 to 5. That's right. Okay, so keep that in mind. Yes, you can integrate that direction, right? We can integrate whichever way we want. It's not always the highest number on top, lowest number on the bottom for your limits of integration. So go ahead, give it a shot. Do it. Okay, do it. And I'll come around and help direct as necessary. I gotta take attendance. It's too late. It's too late. Oh, it's not too late. Minus 2, right. Sine of x, close parenthesis, minus 2. Okay, this is also challenging just to be able to type into your calculator accurately. Right? So.
Fruit. Hey, that's what I got.
Okay, that's encouraging.
What you get?
Yes, but you're wrong together.
Wrong for the right reason.
Let's be different together.
What you guys did? Sounds like a flow.
UK politicians
Oh, okay.
It's like, let's be wrong together.
Sounds like a flow for like a mental illness.
Okay.
It's like an insane asylum, like, you know, they write encouraging things like above the doors and stuff. It's just like, let's be wrong together into the spongy room. Is that like a real thing?
Oh.
Like, insane asylums have rooms that are all like cushy.
His has a pretty tight period. Yeah.
Alright. You know how to look how to change it? Oh, I'll show you here. I mean, if it changes,
Scientists create interesting comments in the past.
his office is like,
I don't trust that. I would never use those.
Okay, don't forget to then also.
Wait for them and your economy before.
That change. Yeah, but
I had a 20% increase in pressure and a 40% increase in volume.
Volume? They're huge. You see what it is filled with water?
Volume as in how much you can minimize.
Yeah, I know.
Yeah, I definitely have a problem with my volume.
Damn it, overflow.
Dude, have you ever seen a condom full of like liters of water?
Yeah, condom challenge is hilarious.
Yeah. A liter.
I
That's not
don't know
a
about
problem
you.
that I
You're probably a
have.
doctor, I mean,
It's
and, what'd you get?
scientific notation.
No.
You're very wrong.
I got 3.
Yeah.
Volume.
Okay, here's your question. So you have two open parentheses.
You can use it afterwards, text a new
Right,
line.
so the outermost parentheses is for the
Wait.
integral thing.
It's like a rug over your shoulder, like a stick with the
Yeah,
rag on the
yeah.
back.
You close the table in the parentheses and also close
If
the square
we're,
root
you know, she's
parentheses as well.
pregnant, use it to move out.
Get you back up.
I want like a condom made of like some
Oh, it is.
like
Whoa, what is this?
alloy that's like
Ew, that makes you feel good.
It's like that
stronger
Tin Man
than
on you.
steel. No, but it's like you didn't do it until that.
Okay, you know what, we need to set up for talking about this. Don't ever say the words rubber and soft in the same sentence.
I think probably recorded.
So what was that you were talking about?
I'm definitely going back and watching this video.
So for example, you just go.
Wait, is there anyone after us today that's going to be watching this video?
Yeah. No.
What'd you get? I got like 2.9.
Probably not.
Yeah, I got 3.
Yeah. Well, you still haven't had it. Okay.
It was 2.999, so it adds to 3. Oh, wait, is it
Like
3?
7th grade English.
Yeah.
What'd you do? I
Yeah.
got like 3. Like 3, that's good. Yeah, it was like 2.99999. Good, good job.
Can I play as your team? Come on.
You okay? Go look at mine, let me know. Anyone else having trouble?
Yes.
Let me play.
Yes?
Let me play. Let me play.
No, you can't.
No,
No, fourth and
Second quiz.
You gonna go for it? On the ball. On the ball.
All right, here's the integral that you should have set up. Here's the setup. Okay, to simplify that, we can then say, okay, f of 9 we know is 3. We're going to add to that this integral from 9 to 5. Okay, so we're going to take this initial amount of capital F. We're going to integrate the rate of change from 9 to 5. We're going from 9 back to 5, so that's why we're integrating backwards here. That's okay, we can do that. We're going to go backwards, okay? Because that's our initial amount. We're ahead of where we want to be, so we're going to integrate backwards and accumulate that rate of change, accumulate the change here to add to the original amount, and that'll get us back to where we were here, which is still going to be about 3. Okay, when you actually do that, it's like 2.999 if you truncate, but if you round, it's actually like 3. Yes.
10.
Yeah. You got 3.000 exactly though? I'll come take a look at that. That's the idea. All right, we're gonna do one more here.
How do you know that,
I'm gonna have you guys try one more here. Okay, last one. Go, rest of them know.
yeah, how do you know that,
calculator.
you're integrating from 9 to 5? Is it just the order of the problem?
It's because, okay, question is, how do we know that we're integrating from 9 to 5, where pretty much every other integral that we see, we're integrating from the lower number to the higher number? Why, in this case, are we integrating from 9 to 5? Brandon?
You're trying to find f of 9 already given f of 9.
So we're at f of 9. Our initial quantity is at 9. We have to go backwards to the 5. So we're integrating from 9 to 5. From 9 to 5.
Alright. So you just assume that whatever value they're giving you is where you're starting.
Yes, that's because that's our starting point, because we have to have some place to start. That's our starting point, and then we can integrate backwards, just like we did here. Right? We were told f of 2, capital F of 2 was negative 3, so we started at f of 2. We wanted to get to capital F of 5, so we go from 2 to 5. Integrate from 2 to 5. Okay, last one. Here we go. And actually, yeah, okay, I'll write it up. All right, here we go. Mr. Wid is baking cookies.
Oh my gosh, this is
Chocolate chip cookies, my favorite type of cookie.
Roommate.
Mr. Witt is baking cookies.
Did you come up with this with your roommate again?
At a temperature, this is, yeah. His problem says he's baking cookies for his favorite calculus class, and then he always likes to, when whichever calculus class, because he has like two, and so he says whichever calculus class he teaches it, he always tells his class it's the other class that he likes more. He likes to tease them that way. All right, anyway, Mr. Witt is baking cookies at a temperature of 350 degrees Fahrenheit. All right. He then takes the cookies out of the oven.
Plot twist.
He then takes out the cookies and burns his mouth while trying to eat them. No. He then takes out the cookies and turns off the oven.
Hey, what rate does it cool down at?
And that is at time t equals 0 minutes. So we kind of like start our calculus stopwatches there, our student stopwatches right there. Okay, and so time 0 is when that is. The temperature of the oven is changing at a rate of negative 110 e to the negative 0.4 T degrees Fahrenheit per minute. All right, that's the rate of change. The rate of change. So if you plug in a time t there, that doesn't give you the temperature of the oven at time t. That gives you the rate of change of the temperature of the oven at time t, right? This is the rate of change of the temperature. Yeah.
I get why pi is such an important one because that's like circles and stuff.
Yeah.
Why is E like such an important one that we use?
It has to do, I'll tell you in a second here. So to the nearest degree, what is the temperature of the oven at time t equals 5 minutes? Okay? Question.
Should we also write that the equation to find the temperature is the antiderivative of rate of change? Is that
Like the initial, like you need to like write that initial kind of generic thing, like
Like the
like
equation.
this.
No, what I mean is like, should we assume that whatever equation we were using to find the temperature is the antiderivative of the equation written?
That was only for these other problems because they were like more abstract. We didn't have any context. In the
Okay.
context here, if that's the rate of change of the temperature, then you can integrate it to find the net change of the
Okay.
temperature. You can assume that, yeah. Okay. But Connor, the idea is that E is a number that shows up. I mean, I think it originates, or at least where I first learned about it, was in interest, like how interest compounds, and it's like. But basically, we're just using it as an exponential kind of number. I mean, it's you know how you could like have interest compound like monthly or daily or something like that. So this is like continuously. So which is what would make more sense because you know the temperature is changing at a continuous rate, not at a like. Once a day, it's like, oh, now it drops 5 degrees. Now it drops 5 degrees. It's changing at a continual rate. So I think that's why we use the E there. It's kind of representing a continual decline, but an exponentially continual decline. I don't know if it's exactly right or not. It might not. But again, for the sake of the problem, this is what it is. So.
That doesn't make sense.
It does make any sense at all.
Wait, should we add?
Yeah.
Okay. So go ahead. Get your answer there, please.
That doesn't make any sense. It doesn't make any sense. Yeah, I think it is add.
Why though?
You know, to be quite frank, I don't know. We're just gonna go with it.
Just go with it.
That would make a lot more sense.
But that's because we add. Yeah, that makes
Okay. So this one's a little bit nicer to type into your calculators. This is a little bit nicer to type in your calculators.
Oh, what the hell?
You know what?
That is the right temperature.
That'd be so nice.
Oh,
In an AP,
Interstellar.
in an AP physics class.
No, I'm telling you, he's gonna make you want these for the 12 videos.
Yeah, there probably was more videos.
Where you see that from?
What was that one?
What are photos for this video that they were called?
Then he shows me how it's done.
They're literally like, oh my, it was horrible.
It was like start in like a college, like,
Classroom.
room, like,
Well, I got the answer, that's not.
And then it literally just said, like, saying math equations, like, and like formulas, and like.
So there was no, like,
It had a special
entertaining...
It was all.
So we're just watching episodes of like the Cosmos with like Neil deGrasse Tyson.
Yeah, I remember that one.
How like the fundamental principle that should change.
That's probably the best one.
I
I really wanna know what they were called.
Oh.
It's like a laser talk explaining all that stuff.
All right, so we have an answer yet?
I do.
I do.
So what did you get, Joey?
I got 112.
112? 112? 112? 112? No one got negative 237.783?
No, but I did get 5.
That's what I got the first time. Oh, no, it's not. Never mind.
Alright, I have a question.
So, okay, let me say it and I'll get to questions, okay? So, are we all okay with that? 112?
Yeah.
Okay, so 112. Well, what are we going to be integrating here? What are we integrating from what to what?
0 to 5.
We're starting at time t equals 0 is when the oven starts cooling. We're integrating to 5 minutes. What are we integrating? What's our integrand?
The rate of,
What's our integrand?
the rate of,
The rate of change of the oven's temperature, right?
yeah.
Okay, so negative 110 e to the negative 0.4 t dt. So we integrate that. Okay, question, Anna, yeah? 121. All right, so, right, it wouldn't make sense if it got hotter, right? But we'll get to that. Okay, so hang on. So negative 110 e to the negative 0.4 x, okay, comma, x, comma, 0, comma, 5. Okay, so did you type it in this way? Okay, so you did this. So let me just try it this way. So you did this. E to the negative 0.4. Oh, negative 110, sorry. Okay, is that what you typed in? Is your Y1? Okay, you see your mistake? Okay. You did type it in that way? Okay. All right, so we hit enter, and we get a negative temperature. So wait a minute, though. Can we have a negative temperature oven? I guess so.
It's called a freezer.
But what's really going on here? Why is what am I supposed to do? Right, the temperature of the oven started at 350 degrees, so we had an initial temperature already. We're going to add to that the accumulated change in temperature. Yeah. Now this number should make sense because what happens to the oven after you turn it off and you
It cools.
it's 350 degrees, it cools down. This is the net change in the temperature from the original 350. So we're going to add 350 plus that negative 237.738, and we get approximately 112 degrees because it said to the nearest degree Fahrenheit. Okay, 112. Yes.
So can you set up like that problem? Would it be f of 0 equals f of 5 to that thing, or f of 5?
It would be capital. It would be, I guess, yeah, capital F of 5 plus equals.
What is that?
Do you start with where you're trying to define?
Capital F of 5 equals capital F of 0 plus the integral from 0 to 5 of our temperature, rate of change in temperature, negative 110. So, right, why is that? We started F of 0, right? We were given that piece of information at 0, temperature is 350. Okay? And then we're going to capital F of 5. We want to know what is the temperature at 5. You see the difference there? Okay. And that's integral from negative 110 e to negative 0.4 t dt. All right. You girls okay? Okay, you fixed what you had wrong? Okay.
Pointing around me.
I am pointing around you. Okay. So, other questions? That's right.
Double split experiment.